The rest of the semester, we're going to be working with continuous probability distributions. Now, previously, we'd been working with was discrete probability distributions, and as we discussed earlier in the semester, back at these early slides, you can see we looked at discrete random variables were variables that were countable, whereas continuous random variables were variables that were measured. So applying these criteria, we'd seen, for example, that how many students were in class today would be a discrete variable, whereas how many miles students drove to attend class would be a continuous variable. Now, the previous sections we worked at focused on these discrete random variables, data that's countable. However, much of the interested in is continuous data, data that's measured. So we're going to be working on this type of data for the rest of the semester. Now, we have two different types of continuous probability distributions. So when we're looking at these, we have what we call a uniform, or we have what we call our standard normal distribution. So when we're looking at these, they both have continuous random variables. However, in the uniform distribution, the variables are distributed evenly over the range of possibilities. This means that any one of the possibilities is equally likely, and it produces the rectangular distribution that you see here on the left. A normal distribution, values are distributed in a bell-shaped curve over the range of possibilities, and it produces this bell-shaped distribution that you see here on the right. Now, there's a couple of things that are similar between these. Both of these have what we call a density curve. The density curve is the graph line showing the probability distribution. So here it's the red line for the uniform, and under the normal distribution, it's the blue line. Okay, so in both cases, we call that the density curve. All right. Now notice that every point on the curve must have a vertical height of 0 or higher, so it cannot dip below the x-axis. So for the example here on the right, looking at the normal distribution, we can see that the ends approach but never quite reach 0. So they would be 0.00002, but still not quite 0. The other factor that's similar between these that is really important is that the total area of the curve must equal 1. And you're going to find this is going to be a very important part, so keep this in mind as we move forward. Okay? There is a direct correspondence then between area and probability. And this is what we're going to draw upon for making our probability predictions based on using the distribution. So, notice that the total of 1 on our probability of possibilities. Remember, all probabilities go from 0, as in it cannot happen, to 1, as in it's certain happen, which means that all probabilities for an event sum to 1. Notice that 1 is the exact same as the 1 under both the uniform distribution and the normal distribution. So there's a direct correspondence between the area and this is so important that I suggest you put it in your notes, draw circles around it, arrows at it, whatever. This is going to be a key part for being able to move forward for the rest of the semester, is this connection between the area under a distribution, a density curve in a distribution, and the probability of the related event occurring. So to kind of get an idea of this visually, we're going to work first with the uniform distribution. So although we won't be using them very much across the rest of the semester, the uniform distribution is kind of an easier way to visualize this connection between area and probability. So here we have our hypothetical situation of a friend who's often late but never more than 10 minutes. So here we're going to have our x is going to represent the time from when you were supposed to meet your friend until they actually arrive. So we've got our variable specified, and they can be anywhere from 0, which is right on time, all the way up to 10 minutes late. So the distribution would look just like this rectangular distribution here on the right. Now we want to find the probability that your friend will be at least 7 minutes late. So this is the problem that we're solving for. So the first thing is we want to write this out in probability terminology. Right, so here we have our x represents time from when you were supposed to meet your friend until they actually arrive. Values can range from 0 to 10. And we're solving for is the probability of wait at least 7 minutes. So that's our probability. Now, the steps we want to do is we're going to want to designate the related area in the figure, and then we're going to apply the formula below. So for a uniform distribution, we can apply this formula of the probability of a single event multiplied by the sections in the shaded area. That's because each single event has an equal likelihood of occurring. So Here's our example of our figure. We've shaded in the designated area from 7, 8, 9 to 10 minutes. Okay, so it's shaded in red. And now if we're looking at our probability of a single event, that's going to be the total area, which in this case will always be 1, because remember, area is all 1. And then we divide it by the total number of sections. Here, if we're breaking this down by number of minutes, as we've indicated at the bottom, then we're going to be dividing it by 10. Okay, so our area of 1 corresponds with the area in the figure, and then we divide it by 10, 1 divided by 10, and we get 0.10. So this is the probability of a single event occurring. So we're going to take that, and we're going to times it by the number of sections in the shaded area, which in this case is 3. And we get 0.30, or 30%. Okay, so the probability that you're going to have to wait at least 7 minutes for your friend to arrive is 30%. Notice here that 30% of the area is covered in the red, representing the probability of your friend being 7 minutes or late or more. So, and notice that 30% of that area then corresponds with a 0.30 probability. Okay, that's why we start with a uniform distribution, because it's easiest to see with a uniform distribution because all possibilities are equally likely to occur. However, keep in mind these same principles are going to apply for the normal distribution. Okay, so although it's going to be more difficult to visualize that with a normal distribution, all the principles that are true for the uniform distribution that we just looked at are also going to apply to the normal distribution that we'll be using for the rest of the semester. So make sure you're clear for yourself this correspondence and the fact that the area of equaling 1 is set at 1 because that corresponds with the 1 of all possible events occurring. This is going to be really important for some of the computations that we're going to do later.